guys, I'm Shubham Agnihotri, and I am a data scientist in day and a gamer at night, and somewhere in between, I do quantum in both the states. So I'll get started. Let me know once you can see the screen. How can I share the screen? Yeah. Mm, Yep, you should be able to see the screen now. Perfect. Yeah. The font. So okay, it was a very good session on cryptography. So what these guys also covered was some basics of quantum. So I'll just slightly list few one-liners which will be requiring, uh, yep, which will be requiring right now. Just and I'll be covering them in detail when we move down, like when we kind of cover the concepts. So one thing is we have something called as what exactly is quantum? Quantum is the smallest physical entity, the smallest possible unit in any physical entity. Then what exactly is a qubit? Like how we have in classical computers, we have bits. So in quantum computer, we have something called as qubits. These qubits have a property which is very special, and because of that, we are able to perform exponential operations at a very polynomial time. So that property is called superposition. So what that property allows the qubit to be in both the states. Now let's say a bit can either be a 0 or a 1, whereas a qubit can be in both the states if it's not measured. And then we have something called as the entanglement. What exactly is the entanglement is when we have a qubit and another qubit interacting, and that is what is entanglement. I'll be covering that when we come down to quantum data, which is one of the crux of quantum machine learning later in the session. And then we have the collapse of the wave function. So once we perform the operation and we try to measure it, the bits kind of lose their superposition property and they are forced to choose one state, and that is what uh, we see when we measure it. Like we get just one state. So that is what is the collapse of the wave function. Yeah. So this is a very like this assumption was for written a long time back, but yeah. Uh, so why exactly we need quantum computing and what exactly is lacking in the classical machine learning? The first question which one should be asking is, now let's say I have my phone. Like it takes hardly a second to unlock my phone using facial recognition, which is again a classical neural networks example. So will quantum computing or quantum neural networks will be taking over that? Honestly, no, because these are something already state of the art which are being developed, and these are the problems which are already solved by the current systems. So these are not the problems which will be replaced by quantum machine learning or quantum neural networks. There are a lot of very difficult problems where the classical computer system says something like this. It's not a scene. Yeah, it says oh, out of memory. Yeah. So there are two reasons for it. It says out of memory, saying that there's a huge amount of data which it cannot process. Or let's say it's not that capable, or the computation itself requires a lot of time, and it's not able to do it in a polynomial time. So these are two such places where quantum machine learning comes into play. So to be in a very brief example, like to short it down in one sentence, quantum machine learning is used in such places where we have, let's say, a finite input and a finite output where we have infinite possibilities in between. So, to explore those infinite possibilities, we need something which is very fast enough so that it can be done in a polynomial time. I wouldn't say real time. Real time is very fast. A polynomial time. And yep. So quantum machine learning is built on two core concepts. Yep. One is quantum data, and another is hybrid quantum classical model. So, yep, it is made. Yes, exactly the same thing. It's something like it is used to solve NP complete problems or kind of address NP hard problems. So let's say an example of this is again an application. Now you talk about the COVID-19 situation. Right now, like after so much time, Russia claims now that they have came up with a vaccine. So if we had a quantum computer which was good enough to run a proper ML algorithm, so we could. So what exactly? Like even there were a lot of research going in the reinforcement learning area for AI to develop the vaccine. So what exactly happens in this is you have a molecular structure and then you try to break that structure by generating another structure, kind of fitting it so that it breaks. To kind of generate that structure, you have n number of possibilities, and the current systems were not able to process those many possibilities. So it's like you need to cut short with your previous knowledge or your assumptions, and to try to see, okay, if this should work or this should work. And in that way, it kind of took a really really long time, and I'm not still sure whether it was the AI which developed it or it was the proper research which did it. Uh, so yeah, this is one place where you can see this. So this is one place where machine learning comes in. Um, yep. Yeah. So let's move on to the crux of uh, quantum machine learning, which is the quantum data, and it's very beautiful. Honestly, it's like if you are from an ML background, you know how much data is important for a machine learning algorithm. So, and if you're not from a ML algorithm, I'll just state one sentence, which is theoretical, very true. It says if the data is good enough, then no matter what machine learning algorithm you're using, you'll get the same accuracy. You'll pretty much get the same accuracy. So that is why good clean data is important. And all the let's say if you talk about neural networks are data hungry. Even if you talk about classical machine learning algos, yeah, they require a lot of data. So this is quantum data is one such form of a data which is which exhibits the property of superposition and entanglement. I'll explain you through diagram. Not diagram exactly. I'll just give you a walkthrough of it, kind of. Yep. So now let's say if we have a two-bit classical system. Sorry. Let's say if we have a two-bit classical system. So it can either be one or it can be zero. Like one bit can be either a zero or a one, and the same goes for another bit. It can be either zero or one. So the total number of possible combination can be either 1 1 0 0 1 0 or 0 1. So in a classical bit system, let's say if it's of 2 bits, we can either be in this state or this state or this state or this state. Whereas in a quantum system, we can be in all these states at the same time. I'll explain you how. Now, one qubit can represent 2 bits. That is, it can be either zero, it can be partially zero and partially one. So so it's like one bit can be zero or one. One qubit can be both. So if it comes to 2 bits, it can be this possible combination, whereas 2 qubits can be partially in all these 4 states. And now let's say if we go with 29 qubit system, 29 qubit classical system can have approximately up to 440 million bit, 440 million possible combination of, let's say 440 million data points. So let's take it in this way. This is kind of a very, very I wouldn't say it's a technically correct answer, technically saying that it's 540 data points, but just for the understanding, we can say it's, let's say, 540 million data points. So what qubit says is, because I exhibit a property of entanglement and superposition. So when these 29 qubits get entangled and are in the quantum realm, that is, they have this superposition property. So this much amount of data can can be represented, like the qubit can represent this much amount of data at one point of time parallelly. And that is the beauty, that you have so much amount of data, and which a classical computer cannot even think about it. Please also share any research articles. Sure, sure, sure. It's there in the references down. Yeah, yeah. So yep. Yeah, so this is what the example I took. So I can explain you one more example of superposition. So what exactly it happens is, let's say you have two wires. It's again a very vague example, but it's just for the people to. It's a good example to understand. So I don't want to go into much of a technical detail on the 101 session. We'll be covering everything in detail. So it's just for to get the basics right. So let's say these are two wires. So one wire takes 0 and one wire takes 1. Let's say, okay, I wrote it up kind of inverse. Huh? So then we have a qubit that says I can take 0 and 1 both at the same time, something like that. So that is what exactly is what. Oh, this is exactly the power of quantum data. So now the next question should be coming in your mind: what exact? How do you generate this data, and where do you store this data? Because if we can represent two rays, like we have 540 million bits represented parallelly, and so where do we store it, and how all these things happen? So currently, based on the current technology, we don't have any. Okay, what exactly is quantum data? Quantum data is a data which is generated by a quantum computer or is generated by a quantum mechanical process. So it is termed as a quantum data. So okay, I'll answer that later. Yeah. Um, so yep. Hmm. Where was I? Huh. So currently, what the tech right now is that any external quantum data cannot be fed into a quantum computer, because they haven't found a way yet. So what Google did was to show that there was a Google supremacy experiment. So what these guys did is, the quantum data you can use is when you generate it using the quantum computer. So that's what these guys did. They generated the quantum data and then used that data to show that we can do something which in polynomial time, which would take around 10,000 years for a classical computer to do it. So this is exactly how this thing works. So you have a circuit. This is like we'll be going in depth in the later parts of this series. I don't want to go much into detail of these circuits, what exactly these are, and how do we develop these. So what happens is that you give the input. This input is given to this pure hardware. It's like these are chips. These chips convert that kind of classical data into the quantum state, which can be represented in the Hilbert space, and then it is given to the quantum model, which runs in the quantum computer, and that quantum model then gives an output, which again goes to a classical model, and then a classical model kind of gives us the final output. So it's something like it's a uh, both the guys are trying to get, they take advantage of each other. You can say it in that way. So yeah, yes, how the data and where exactly it is stored right now. Uh, Quantum hardware is one such research which is going on, because we are not able to even stay in a quantum state for a very long time. So storing it is really difficult, and because the quantum state itself lasts for a fraction of seconds. So we because let's say we have billions of data points, and we are just able to run it over for a fraction of seconds. It kind of we won't be getting anything. Like we will definitely be getting something out of it, but it's not something which is ideal right now. So quantum hardware is where do we store all these things? It's still under research. There is no proper hardware which is there in the market or commercial, or is commercial, where we can use it to store this high amount of data. So okay, coming to what classical hybrid. hybrid quantum classical model. So this is a very nice example. So it's like it's taken. If you are a Dragon Ball Z fan, then you definitely know what it is. So what happens is you have this guy on the left, you have this guy on the right, and to defeat a very big enemy, what these guys do is these guys fuse and form something incredible. So like combining both the powers, and that is what is hybrid quantum classical model. So what it says is, okay, everyone knows. Okay, if, to be on the same page, I'll say that quantum computers are amazing, but they won't be replacing any classical computers because, yeah, that's true that quantum computers are very good in performing matrix operations. They can perform exponential operations in polynomial time, but they cannot beat classical computers in just copying the data. So every hardware has its own advantage, and that is what hybrid quantum classical model tries to leverage. We'll be doing the we'll be doing. Thank you so much. We'll be doing. Just put it up. It's kind of distracting. Sorry. So yeah. So yeah, we uh, did this diagram shows the current the you can say libraries or platforms where you can currently learn or you can develop your quantum machine learning. So for let's say what exactly is quantum CQP ready is that once the quantum computer is commercialized, let's say even if you can use it for using IBM Q, so whatever algorithm you have developed uh, in this, you can directly run it on quantum computer. And so you have various different things like you have Qiskit, you have Pennyline, you have QHash, you have Circ. Circ develops works on simulators. It's CPU only, so it's kind of it in the back end. It takes your CPU. Whereas if you want to go GPU and you want to say key uh, I want to kind of combine GPU and QPU. So you have any lane for that. So right now we are not very much focused. Like we don't want to direct anyone to any of these. It's again dependent on the user which they want to use because all these things are currently kind of trending in the market. Yeah. So yes. So I guess I kind of covered it too fast. So I'll just see if I can see if I miss out anything or not. Yep, these are a proper kind of a definition of what exactly quantum data is, and yep. So okay, there are various currently algorithms which are being developed in QNN, but yeah, there are various algorithms which are developed in QNN. But right now we have not been able to kind of get the proper, uh, the exponential speed up or to see that purely coming out because we don't have the quantum hardware to run this. So we have QSPMs, we have QMIN algorithm, we have QNNs, uh, which are kind of the neural network implementation of in quantum. Then we have QGANs. QGANs is a kind of a subset of QNN because it's again a neural network running in the backend. So yep. So Q means Rajshekhar will be taking. So Rajshekhar, can you just brief us on what exactly Q means is?
Sure, Shubham. Hi, everyone. I'm Raj. I'm just going to give a brief overview about Q-means algorithm. So basically, Q-means is like if you look at from a current machine learning algorithm perspective, it is analogous to the K-means, the classical K-means algorithm. So if you have a background on machine learning, especially classical machine learning, you would know that K-means algorithm is it falls under unsupervised learning paradigm. What that means is given a data set, all the data points within the data set do not have any labels. Now, the objective of the classical k-means algorithm is to group the data points into various clusters. And the number of clusters that the given data points has to be grouped is a predetermined number which is given by a user. So the in traditional classical k-means algorithm, there are predominantly two steps that we try to do. The first one is to label the data points which do not have label upfront. So we tend to label them. When we are trying to label, what we mean by that is that we are trying to assign each data point to a particular cluster. And once we do that, we recalculate the centroid for each of the clusters. And the centroid keeps updating itself. So we repeat the process of labeling the data points and finding out or estimating the new centroid. So we repeat these two steps over and over again. So it is like a iterative process. You can compare it with the expectation maximization algorithm if you're aware of, in the classical machine learning world. So by doing this iteration, in the end, what we'll get is a bunch of clusters, and the number of clusters, as I said, is predetermined, uh, given by the user, and we get the data points segregated into groups or clusters. So Q-means, which is a quantum flavor of the classical K-means, does very similar job. So its objective is to, basically make all the data points into various clusters. Now, the high-level steps that I mentioned in classical K-means are same in Q-means as well. It's just the way that we do those steps is differed because we use the quantum routines. And unlike the traditional classical k-means, the amount of data points in the data set is very huge in q-means. That is expected, right? Because we want to use the parallelism in q-means or quantum realm so that we speed up the process. But though we are trying to say that we are trying to speed up, it really doesn't, you know, at this time, based on the available hardware, we are not, beating any of the performance aspects with respect to time of the classical k-means, but we are really achieving some sort of a robust model, you can call, when we compare with the classical k-means. So what I mean by robust is, we all know that the quantum realm brings us some sort of uncertainty into the picture, especially from randomness perspective. So the q-means algorithm tries to address this by, making the algorithm, the routines or the steps that I mentioned, the label assignment and the centroid estimation in forming those groups is perturbated with the noise element, so that they become more robust and try to handle the huge amount of data with the foundations of that uncertainty caused by the quantum realm. So basically, you can say that it's analogous to the classical k-means, but works on a more high dimensional data space, uh, ultimately giving the same meeting the same objective of, you know uh, grouping them into various clusters. So that's the crux of q-means, and we'll go into more details in future sessions on this. Especially we'll go in depth. We'll do a deep dive into each of those steps, probably next week or in the next weekends. Yeah, with that, I'll hand over back to Shubham.
Yep. Thanks, Rajshekar. And I guess Minaki was one answer, right? Yeah. So yes, we'll be covering humans. We'll be covering the circuit and everything. It'll be in the later sessions, not in the one-on-one session, because kind of we as we made it open to us, we didn't want it to go much in the detail of kind of everything, and bombard you with all the algorithms and the circuits and everything. So yeah, it'll be covered. We'll be covering each and every algorithm, and we'll be implementing them, and we'll be seeing how they perform, and we'll be seeing why they are not right now efficient, because we don't have the hardware for it. Like as Rajshekar said, now we have, okay, the quantum cryptography team talked about Shor's algorithm. Shor's algorithm says I can crack RSA, but do we have the hardware for it? So like yesterday we had a call with Urvashi Sinha. What she said is, yeah, we can crack RSA using humans, but we need using Shor's algorithm, but we need something. We need approximately 1 million gates and 4,000 qubits to do that. So which is very very far right now. But can we do that? Yes, we can do that. So in the same way, can these algorithms create a huge difference? Definitely they can. So, coming on to what exactly is SVM and what is QSVM and what is SVM. So, if you're from a machine learning background, you know what SVM is. So, what SVM tries to do is that you have a data set in n-dimensional plane, and what it tries to do is it tries to find a hyperplane. Hyperplane can be a plane falling in different dimensions, and then what it tries to do is it tries to segregate them using those kind of planes. So whereas SVM has a problem of let's say if dimension goes really high, then the classical SVM is it's like I'm not able to do that because it's something because everything happens in a classical computing is in kind of a serial order as compared to a parallel execution. I don't mean the hardware parallel execution. What I mean is the conceptual way. Because when we come to the quantum computing, we have things in we have the data points represented parallelly, and then we have the person running really parallel. So yeah. So what exactly is QSVM? It's just very similar to SVM. If you know SVM, then it will be easy for you to understand. So what happens in QSVM is you have something called as quantum feature maps. So what these feature maps do is they convert the classical data into quantum data. Now, as I previously discussed, that there is not much. There's no way right now to input any quantum data to input any external quantum data to a quantum computer. So what we do is we use classical data and we try to convert it, and then use that data inside a quantum computer to uh, you know make some predictions and to give us outputs. So that is what a quantum feature map does. So in this, it converts the classical data into quantum states, and then these states are represented in the Hilbert space, and then once we get that states, what we do is we build kernels out of it. What exactly are these kernels? So kind of let's say kernels are filters. Kernels are filters. So these filters, what they try to do is they look at this data and they try to segregate this data out of it. Something like kind of the hyperplane equation you can talk. So the kernels act as those filters and then separate these data out and classify the data. Something like that. So this is what QSVM is, and yeah. So coming on to again over here. So, okay, coming on to the quantum neural network part, that's pretty interesting. So, that should be visible. Yeah. So, this and this, if you remove this, is a very classical neural network. It can be anything. It can be even use it to for natural language processing, or you can use it for image segmentation or object detection or image classification or any use case. So it's a typical way how you represent a neural network. But when it comes to a quantum neural network, like even when I was talking about the quantum data, I said that we have a quantum circuit. Then we have some. After that, we have again a classical model, which kind of gives us an output. So this is one such example of that. The what we do is we have a classical model. The initially it's a classical neural network. What it does is these x1, x2, x3 are the input variables. So it can be the input data. It is the input data, and then if you are familiar with neural networks, you know the concept of weights and biases. And the weights and biases are the values of the kernels or the hidden layers inside a neural network, which kind of tries to figure out what exactly the output has to be. Something like, let's say, if we want to do a classification of, let's say, a cat or a dog. So these input will be the image of the cat. Like I'm explaining right now, the typical of the cat. So this thing go this thing goes into this, and then what happens is these values are the pixel values. See. So there's a bit of disturbance in the audio. Could you please check on his side? Okay. Hello. Is it fine? Hello. Hello.
Yeah, it's good
Hello.
now.
Yeah, it's fine now. Okay, perfect. Yeah. Huh. So, 2 minutes. Yeah. So, so what happens here is, yep. Like we have an input of a cat. This goes into the classical neural network, and then we have the concepts of we have the weights and biases. What these things do is these are the pixel values. So there is a kind of a operation which is wi into xi plus b is right now nowadays it's not used because it's kind of like it's like it can be proved that we don't need actually biases now. So yeah, that's something not related to quantum, so I won't be discussing that. So yeah, because over here also you can see that there is no bias over here. So this is, and here the sigma is the activation function. Activation function is just to get the non-linearity. Non-linearity is something because neural networks are theoretically considered as a universal function approximators. So that means you can kind of represent anything. You give it to neural network, it'll figure out something like that. So yep. So what happens is you know this import is being processed. These are the hidden layers. It can be any layer. Now let's say if we go into a normal neural network, there are different types of layers. You have fully connected layers. You have convolution layers. You have depth-wise. You have separable. You have depth-wise separable. You have n number of layers. So you have dropouts. You have batch norm. So it can be any of these layers, and then because it depends on the problem which you're trying to solve, and then these hidden layer acts as an input for the quantum circuit. So, and what exactly the circuit? What are these? These are the quantum gates. It can be any rotational gates. So it again depends on the problem you're trying to solve. And then, so what these things do is that this input goes to this gate. This gate then performs operations. We have the circuit built in. Then once that then when we try to measure that circuit, that output gets stored in another a neural network. So it's like, and then that from that output we try to figure out what the final variable is. So something like okay, in technical terms, you give the input, then those inputs are being processed by the hidden layers. The hidden layers kind of act as an input for the quantum circuit. The quantum circuit are built on rotational gates. Though the sorry the rotation the inputs to those rotational gates are the outputs of the hidden neurons. The gates give you the rotation angle, and then that kind of gives is the output for the circuit, which is again the input for the another hidden layer, and then that hidden layer then again we have few hidden layers to do the processing and do the error calculation, and then we have the final output. So let's say if we go into the kind of the technical term of it, then yeah, definitely one question is how backpropagation works, because in neural network it's kind of the crux, and it is the smart thing, or it is what makes neural network smart. So we have something called as conventional neural networks would lag in the present scenario. Okay, I'll just answer to that in the end, Prashant. I'll answer all your questions. I'll take all the questions at the end. So sorry for that. Yeah. Um, yep. So what happens in the backpropagation is like it's kind of the brain of the neural network. It kind of makes it be smart. So what is this theta? Theta is kind of the angle which, like over here we are measuring the rotation. So kind of this s is a very small change in kind of a positive direction or in a negative direction, something like that. And then that is being calculated. So how backpropagation comes in, what it says is, okay, fine, this is the output and this is the output I was expecting. And what it'll say is, let's take an example of gradient descent. Just yeah, let's say what happens in a gradient descent is, let's say a particle was here. Now it knows that this is the place it wants to go. Means this is the loss. This thing is the loss. So what it'll say is, okay, fine, I'm here right now. What I'll do is I'll do a small change in the weights before it, and I'll see how it performs. So let's say if it says, let's say if it was 0.5, just hypothetically, because it's just for the understanding. So what it'll say, okay, let me try it something at 0.4, and it says, okay, no, I'm going away from it. So I don't want to go in this direction. Whereas let's say it'll try, okay, 0.6. Yes, I'm going closer to it. So I should be doing something which I'm doing right now. So in this way, something like that happens. So over here also, what it'll do is it'll kind of try to measure something at a small changes, and it'll try to observe how's the performance, and then it will kind of tweak the weights in such a way that we get the desired outputs. Yep, and this is called a parameterized circuit. As the name suggests, parameterized means kind of we are giving the input a value. So that's why it's called a parameterized circuit. So we have various applications of quantum machine learning. So one example what I talked about was, let's say, the COVID situation, that if quantum was existing, then we would be able to kind of generate n number of possibilities to try to get the vaccine out, and that would be in a polynomial time. So COVID was long gone if QML was in the market right now, commercially in the market. Commercially means because it should be able to do these mammoth tasks and without kind of losing the quantum state. So which again will take quite a while, but yeah, there's a lot of research going on, and this is the perfect time to get started. Yeah. Then yeah, we have quantum communication channels. So so if you guys kind of attended the yesterday's Urvashi ma'am session, so what she was talking about was something called as quantum internet. So kind of to to get something that into a reality, we need something called as the non-orthogonal states. We need to identify those states which can be used as repeaters and receivers. So kind of we have a satellite sending, or we send the information to the satellite, and then satellite sends it to the local ground station, and then how things get distributed, and where kind of these how kind of how to identify these states which make things really fast. Something like that to be keeping in layman terms. So what is dimensionality reduction? Reduction is something which we were talking about in SVM, because SVM is an algorithm which is really good. But or let's say even if we go for k-means. Okay, k-means is a very good clustering algorithm, but when it goes to when the cluster size increases, uh, it kind of slows down really exponentially. And same goes for SVMs. So this is where quantum machine learning comes in and says, don't worry guys, I'm there, I'll do it in something really fast because of the properties which I inherit. And yep, I guess quantum simulation. Yeah. So yeah, these are some more examples. Kind of exactly trying to because right now let's say we have something called as the collapse of the wave function. Okay, so what happens over here is, from the definition which I shared, what exactly is the collapse of the wave function. Let's go here. Yeah, so all these things happen in the quantum state, and when we try to measure it, let's say I was talking about 540 m bits. So, let's say we have all these things happening in parallel, and when we try to measure it, this thing breaks down, and we get a 29-bit kind of an output, something like that. And this is what happens with something called as the collapse of the wave function. So, we are forcing the computer to lose the superposition state. So, yeah, so there is a kind of again, the enamel can be used in designing the circuits where we can try to figure out a way to view the quantum state, something which is currently in research right now. Then yeah, this is again kind of to to try out different combinations to test to bring out something of a new material. So something like how what chemical simulation was kind of a drug discovery to find out something which is very stable and which can be, let's say, which has high temperature, high conductivity. So we need to run a lot of simulation. We need to try a lot of. We have infinite kind of possibilities, and those possibilities currently cannot be tested out on classical computers. Whereas you can use all these things here. So how to get started? So firstly, if you are watching this session, then definitely you are at the right place. Then secondly, yep, do you need machine learning to understand QML? And short answer, yes. And if you want to go in a bit of a long answer, I would say uh, it's like yes, because quantum itself is a very complicated domain, and here even all the algorithms which I discussed were based on the algorithms which were kind of developed. Yeah, there is definitely a possibility of research where we try to develop something which is not existing in the current classical domain. But yeah, that thing happens. That'll take some time, and because if you're not new to ML, or if you're new to ML, or you don't know much of these algorithms, then first you need to understand these algorithms, you need to understand the quantum, and then you need to understand how these things interact in the quantum domain. So yeah, it will be complex, but definitely you can do it. And so yes, ML is required. So the book for QML, I would ask Nishmita to kind of give us a brief on this book. And yeah, Nishmita, over to you.
Yeah, Shubham. Thank you. Hello, guys. This is Nishmita. I'll just give the overview of the book Dancing with Qubits, which I have been reading from the beginning of this apprenticeship. Um, yeah, this is the book written by Robert Souter. He's a 37-year veteran of IBM. Currently, he is the VP, IBM Ecosystem Development, IBM Research. He is an innovative leader and as well as technologist with strong experience in blockchain, AI, quantum computing, etc. This is a very nice book. Everyone who want to learn the quantum computing, they should read this book, I say, because this takes from the mathematics and then it will go to the quantum computing. It will set the in the book he has set the base for quantum computing. Like he has explained linear algebra, vectors, trigonometry, whatever required for quantum computing in the first half. Then he has explained quantum computing. That is also again basics, gates, all those things he has explained very nicely. Um, this is just an overview of the book I'm saying now. I'll anyway go to with the chapter by chapter overview in the coming sessions. Thank you.
Okay.
Thanks.
Thanks, Nishmita. So, yep. So, what exactly are the skills required to kind of get started on this? Firstly, is yes, Python, because most of these libraries are written in Python, or kind of have a Python binding. So, and Python is very easy to learn because even if you talk about the machine learning side of it, you have almost everything in Python. Though the backend is written in some different language. Now, let's say if you're familiar with TensorFlow has a backend in C++, whereas if you look at the GitHub repo of TensorFlow, it says 50% is in C++, whereas the rest is in Python, and that Python is just a binding. So but because Python is very easy to learn, it's very adapted right now. So I wouldn't recommend anyone to go for going with the uh, understanding of how to implement them, because that's more kind of a job of a developer than because we need to use them and move forward and build applications on that. So Python is one language which is a must. Then you have yes, you should be familiar with machine learning algorithms. Let's say because let's say if I was talking about SVM, and you take QSVM, and then because even if you read the research paper of QSVM, they have compared it with SVM, and then you figure out, okay, what exactly is SVM, and then because the paper itself will have a lot of formulas of the quantum thing, or the quantum realm, and then firstly decoding that will take time, and then you will be kind of in you'll be kind of lost. So yeah, honestly, so it's better that you have an idea of machine learning algorithms. Then if you are learning machine learning algorithms, these are the things which you should be knowing. And yeah, and yes, um, and one more thing is you need to know the basics of quantum. Okay, how things happen in quantum, what the gates are, and how can we kind of leverage the power out of it. So yeah, these are some few different libraries which are kind of available. It's open source, you can use it. So it depends on you and anything you can like. So they pretty much do the same thing. It's like few of them run on simulators, whereas a few of them run on QPurity things. So, but anyways, uh, let's say Q Sharp was developed by Microsoft, so that definitely they'll be trying to move it to a place where you can be QPurity. So choose anything. You have a lot of no, this is something new, but let's say you go for TFU or QSKIT, you have a lot of documentation on that. You have a decent community out there, so that will kind of help you in understanding it. So it's 6:15. Okay, so I'll just kind of give you a small summary of what exactly we discussed, and then we'll be open to questions. It'll take hardly me 2-3 minutes to do that, and then if you want me to cover anything, definitely you can ask. Yeah, Sam, you wanted to say something?
No.
Yeah.
Hmm.
Okay. So, so we discussed what is quantum data. Firstly, we discussed what is quantum, the different properties of it, which was the qubit, superposition, entanglement, collapse of the wave function, what exactly it is. Then we went through where classical machine learning fails, and what exactly is classical machine learning. Let's say we took an example of the phone recognition because it's something pretty fast, so it's not something that a quantum computer will be working on. uh, the quantum computer will be working on, kind of trying to find the solution of coronavirus, or that is again kind of a very small domain. I'm not sure it can, if it has n number of possibilities. So then we discussed on, quantum machine learning is based on quantum classical models. So quantum data is something which exhibits the superposition and entanglement properties in a form of data. And how it's good because it kind of helps us do things. It kind of enables us to have an exponential data process. We can kind of process exponential data in polynomial time, which is pretty amazing. And then we have a quantum hybrid model, quantum classical hybrid quantum classical model. So what it does is it kind of leverages the advantage of both the things. Kind of building a circuit where you don't want a quantum computer to do task which it's not that good at. And we don't want a classical computer to go for processing because you have quantum for that. So this is where we kind of combine both of them, and we leverage the properties of both of them and get the best out of it. We have different algorithms in this. There's a lot of discussion going on. There's a lot of kind of research and going on in a lot of these domains, kind of trying to implement the previous algorithms in the quantum realm. So yeah, definitely in the near future you can see a lot of them coming up here. And then we covered quite different applications. Then why do we? How can we be a part of a QML? How can we contribute? Is how can we learn? Is you know uh, these are some skills which you require, and once you do that, you have a lot of content out there. Even you can be, we'll be having these sessions, so you can definitely come back and we can learn together. So yep, that's it.
All right. Lovely. We'll take a few questions.
Yeah.
KG, you want to add something?
No, just let us answer questions.
Okay.
So in the interest of time, I would like to
All right.
answer questions.
Yep. I see a lot of questions. So guys, it would be awesome if you could come out of mute and ask the question.
Uh,
Yeah, so quickly I can
Shubham,
have.
most of the questions myself and Sadab answered.
Okay.
Still, you can answer. For example, there is one question from
Right now.
um,
From.
So in the meantime, I can just quickly ask one, Shubham, Prashant here.
Yeah.
With respect to the machine learning, for example, if you're talking about the neural nets, and I guess I just got an answer saying that mostly the concentration is the unsupervised learning. But when we look at neural nets, there's more of a stretch and squeeze architecture that we use.
True.
So in such cases, how exactly quantum would be doing it? Because what we're trying to do is we add a lot of parameters and then we add a lot of normalization and as you said, the gradient descent as well, the stochastic gradient descent, many other things that come into picture. So when we try to do that, many parameters get added. So at what point of time or where does it really the quantum would come into picture?
Okay. Yeah. So okay, to answering if you're talking about the unsupervised learning part of it, yeah. Firstly, I'll say okay. First, I'll answer in just yeah. First, I'll answer why what exactly is unsupervised learning, and then how neural networks come in play and how quantum comes in play in that. So if you are a guy from ML, then you know someone called as Andrew Ng and Jeffrey Hinton. So these guys are I was just going through one of their conversation, and then Andrew Ng asked him ki, what excites you the most, and what Jeffrey Hinton says is the unsupervised learning portion of it, because this is a place where is yet to be explored. uh, Quantum, the neural networks currently which you see in the market, or let's say which are commercial, or even in the startups we see, a lot of them are over the supervised learning portion of it. So,
Yeah.
quantum neural networks can definitely become in such a place where we try to build, even it can be used for classification, but we should not forget that the fact that QNNs can also be used for research, to exploring domains which are yet to be explored. So somewhere, kind of trying to leverage or trying to explore the unsupervised learning. Definitely, quantum can come over there. And if you're talking about the structure of how there will be so many parameters, and how do you fit the circuit and then try to get the output of it out of it. It's simply like, okay, the different libraries have the different the way to represent it. So if you go into TensorFlow Quantum, so what these guys have done is these guys have converted that circuit in a form of a layer, like how we have a layer in the network, and then it becomes like a normal network. So these guys have done that way, and then so it's like every algorithm has their its own different way of encoding things into how do you want to represent it. So it's pretty much the same way how you write a neural network, you write a quantum network. Whereas in the quantum network, you need to kind of specify the circuit, what you're trying to build that circuit, and what you want to do with that circuit, and what gates has to be there. So yeah, those things we'll be definitely covering when we'll be going for the quantum and hands-on, and kind of going much in depth on quantum and. So yeah. So did that answer your question?
Yeah. Yeah. So Python, does Python have a quantum package, or is
Definitely.
it only on TensorFlow right now?
No. If it TensorFlow is again built on like it has a Python binding, so you can just do pip install TensorFlow to work. Otherwise, you have QSkit. QSkit is again on Python. All these packages which I showed, I'll just again show the screen.
Skate, Pennyland,
Yeah,
and
yeah.
even TensorFlow Quantum version is also available.
Yes.
Recently, TensorFlow released to Quantum version.
So, yep. How can I
In TensorFlow Quantum is the simulation. It's not the actual quantum implementation.
Okay.
let's say
Okay.
you have something like this. What you can do is, if you want to get started on this, what you do is you just follow the steps. It'll be there in the system. Then again, these are given hands-on onto that. Then you have again, if you go with Qiskit, because this is something which I'm talking about in respect to neural networks. So what does Qiskit say is, we have collaborated with PyTorch. So Qiskit has its own kind of a binding with a PyTorch. So if you look at the Qiskit neural net example, it'll be with PyTorch. So if you are onto PyTorch, you can use Qiskit, and there are various different, like a lot of them. Even I haven't explored all of them. So yeah, so you can definitely have a look on.
Sure, that's great actually. If PyTorch has a implementation from the quantum perspective.
So you can look on to something like Qiskit, PyTorch. Yep. The hybrid quantum classical neural network. There's the Qiskit textbook where they have integrated Qiskit with PyTorch, and they're working on this MNest, which is kind of the one-on-one data set on image classification. So this is what they have tried to work on. Yeah.
So like neural nets have image architectures like ImageNet or AlexNet. We
Yeah.
don't have anything as yet, right? Or in quantum?
Okay. What you can do is you can definitely no,
Not
yeah,
really.
Not yet.
there are not yet.
Yeah.
But those are kind of the classical implementation of it, right? Now, let's say TensorFlow gives you the advantage to use it as layers. So what you do is you write the layers of those, let's say the inception or the ResNet block, and then you add a quantum circuit to it, and then you complete the model. So it's kind of QNN, like it's an inception QNN sort of a thing. But is it real right now? We don't have the hardware to do that, because inception is again a very, very, very big model, and kind of. So yeah, it's still in the research phase. So, but yeah, it can be done. You can build
But we
your
don't have any papers as yet also on that.
Mm,
Not yet. Okay.
not to my knowledge yet. Yeah.
Okay. Thank you, everyone. Thank you, everyone.
So what is one more question, guys? It would be awesome to come out of mute. Any suggestions to learn ML? Okay. Any suggestions to learn ML? There are two things. Whether you want to go with the classical one in the sense, the sklearn one, which is you have the kn and the k means and the clustering, and there's something called as like something which is not the deep learning side of it. Then I think kg and Raj can answer to that if you're talking about the deep learning side of it, because that is where I'm kind of inclined to have a lot of courses online. I would recommend you can check out Coursera. Coursera has pretty good courses where you can kind of go and learn few of them. AntriNG provides one of such really nice courses.
Right. Even edX has some good ones.
Yeah.
In deep learning and machine learning.
Yeah, edX and yeah, definitely AntriNG. That's the beginning I failed for. Yeah.
Yeah. AntriNG is nothing can beat him.
And wrong. Okay.
Cool. We
Yes, Sam. I think we are pretty much covered everything. We can wrap up.